Hello. This is building a simple neural network for classification. This is assignment 3. Python versions and key libraries, Python 3.10.11, TensorFlow 2.10.0, and NumPy 1.26.4. I'm still using the same variation of Python that I was using for the first assignment. Up to this point, I have found no reason to update my variation, because if there has been an issue with pulling any of the information down or using certain external pieces with Jupyter, being on this variation of Python has been the best thing that I can have, because the workarounds are mostly built for these variations, nothing newer. So I have remained on the same versions, and until there is a reason to change, I probably will stick with it. So we're going to get into the assignment. Is this. So we have 3 parts to it. I've simplified it down to just the 3 main pieces with everything in it, and have removed all of like the extra stuff or any tests that I ran on my own or separate pieces. So we have the imports here. We have the load data. We have the loading of the data from that I have locally, trying to pull the data from the externals with the security keys and everything. It's tricky, and I've noticed that it's been a little bit problematic, and sometimes it just doesn't work. Flat out, it just will not work. So we're just going to keep using local data, just download it and just keep it in the files. So right here we have the train and test sets. We have them for the 784 dimensional vectors. And we have the one hot encode, and then we are confirming the shape of each of them, which we can see right here. The 78410, 78410 is exactly where we want it to be. That is what the assignment asked for it to be in. So that is what we shot for, and that is what we have. On the next one, we once again have the imports, everything, model sequential, dense, the ReLU, activation softmax, the input shape at 784. Once again, these values, they're starting to add up a little bit. For compile, we use optimizer atom. Loss is categorical, cross entropy, and the metrics are for accuracy. So that way, when we look at the model, right here we look at the results, we have the shapes in exactly where they should be, and all the values add up as expected. There's no problems. All the data is being worked in the correct format, so that way we can then use it to build these models into a more accurate variation. So now we're going to come down to the final product, or the kind of the previous 2 statements and sections. This is kind of what it all adds up to. As you see, we have the imports, once again, all that, files. This one pulls from the online one, because this, I don't know, I probably should look more into like the local data that I downloaded versus these online files. When trying to replicate this with the local files, this is the one occurrence where I have the exact opposite reaction. So I did pull from there, and here we got the XY train, XY test. We have the reshape, all that, the one hot encode, and then we have the building the model again, and now we have the compiler with the evaluation and then the testing of the accuracy afterwards. So this is like the validation piece of the puzzle. So here, downloading the data. You can see right here, it runs the, we have the 10 different runs right here. And then it gives us a very nice, at the end, a final test accuracy. So we can see the accuracy range over time. And then this is what we got at the end. We have 0.9816. Now, when turning that into a percentage, that's a 98% accuracy rating, which for majority of things would be a really good percentage to have. I mean, 98%, if you're aiming at something 100 times, you're hitting it 98 times. The only time where you'd want that data, that extra 1%, 1.5% is if we want to have this being used for any form of legal matters or medical matters besides just taking like notes during an appointment. Any form of decision making that can come from financial statements and financial gains, especially for tax reasons. You'd really want that higher percentage. That is the whole assignment, broken down into multiple pieces. 98%, which is overall very good for most models.